All right, so this is our first lesson in this unit. Um, and this lesson has nothing to do with the rest of the entire unit. It is completely random, but they put one of these questions on the test, and so I have to make sure you guys know how to do it. You should have learned it in your first year of math, but if you didn't, it comes back up now. And this is when they expect you to be able to show mastery on exponents. So we're just going to run through all of the rules. So this is kind of like a crash course in exponents. If it feels too fast, I do have it broken down into two separate lessons that you could do to like break it apart, but I think you should be able to get it from this one. So first of all, what's an exponent? New equation. So remember, an exponent is technically the little tiny number in the upper right-hand corner. So the little tiny number in the upper right-hand corner. So the 2 in the example below. So in this example, it's 3 with an exponent of 2. They also call it 3 to the power of 2, or 3 with a degree of 2. They all mean the same thing. It's also most commonly known as squared, so this would be read as 3 squared. And the significance of it is the exponent tells you how many times you multiply the number to itself. So the exponent tells you how many times you are multiplying a number to itself. So 3 squared means 3 times 3, which is 9. So it's not 3 times 2. 3 times 2 would be written like this, where they'd be side by side, maybe with a parentheses between them or the little dot for multiply. And this means add 3 twice, and 3 plus 3 becomes 6, because multiplying tells you how many times you add. The exponents tell you how many times you multiply. So then 3 times 3 becomes 9, which means every single exponent, even if it's on a letter, you can break it apart. So like this is g to the power of 5, which I can break apart into, what it means is I take g and I times it by itself 5 times. 4, 5. So these mean the same thing. G to the power of 5 means g times g times g times g times g. So if I did this again with a new example, where I'm just like writing them out the long way. K to the power of 7 means k times k times k, 4, 5, 6, 7. And then because there's nothing between the k and the y, it just means times. And then there's, wait, where's my little time sign? Oh, I know what I did. No, I don't. 1, 2, 3, 4, 5, 6, 7, 8. Okay, yeah, I put 1 too many k's. There we go. Y. So k to the power of 7, y to the power of 3 means you have 7 k's being multiplied to each other times 3 more y's being multiplied to each other. And so now this one has a to the power of 3 all in a parentheses being raised to another exponent that happens to be a 4. So what this means is that I have 4 a to the power of 3's being multiplied together. So there's 1, 2, 3, 4. So the 4 on the outside of the parentheses means I have 4 of everything inside the parentheses being multiplied together. But then each one of these a to the power of 3's becomes a times A times A. I'm going to get rid of the parentheses because it just means multiply. I don't need to have it twice. So each one of these little a to the power of 3's, I'm going to replace with 3 more a's being multiplied to them itself, because that's what it means. And so now, if I were to count, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this one has a total of 12 a's being multiplied together when it looks like this. So what we're going to do with these exponents is we're going to learn the rules of how we can combine them quickly without needing to write them all out. So in order to do that, we have to talk about the giant 1. And the giant 1 is just this concept that says anytime you have a fraction, and the same thing is on top, like 6 as it is on bottom, 6 divided by 6 is just 1, right? So in the same way, as long as it's the same on top and bottom, like let's say it's x divided by x, it is just 1. So anytime with exponents, if you have the same letter on top and bottom of the fraction, after you write it all out, you can cancel them because they just become 1. So I'm going to show you what I mean with this example. On top, we have g to the power of 9, which means g times itself 9 times. 3, 4, 5, 6, 7, 8, 9. Then on bottom, we have g to the power of 4, so that's 4 of them. So now I'm going to zoom my page a little bit so that we can see this better. So because it's all multiplication, every single time, and maybe I'll use pink for this, I have g divided by g on top and bottom. So here's one, a g on top and a g on bottom. They can become a 1. So that looks like a 1 sort of, if you can envision it going straight up and down. And so this g divided by g can become 1, this one can become 1, and this one can become 1. So 4 pairs became 1. Which means if I were to rewrite this, on top I have g. Oh no, what happened to all my 1s? G times g times g. But then the next 4 g's became 1s. So times 1, times 1, times 1, times 1. Because with the next 4 g's on top, they combined with the ones on bottom, and a g divided by g became a 1. There's still 2 more g's after that, though, so I have to add times g, but there's no more g's on bottom. They all canceled away and became these 1s on top. So if I were to try to simplify this out, anything times 1 is just itself. Like 5 times 1 is still 5. X times 1 is still x. And g times 1 is still g. So g times g times g times 1 times 1 times 1 times 1, it's like the 1s don't even need to be there. So really what I have is g times g times g. All the 1s don't even need to be there. And then times g times g. Because when you multiply by 1, it just becomes the same thing. So we don't even have to think about them. So then if I were to combine these together now, that becomes g to the power of 1, 2, 3, 4, 5. Because there are 5 g's being multiplied together. So then there's a rule for this, but we're going to talk about it in a minute, and I'm going to show you another one. This one's a little more complex. There's more parts. So g to the power of 2 means I have g, no, g times g, and then x to the power of 7 means x times x times x times x. That's 3, 4, 5, 6, 7. And on bottom, I have g to the power of 4, so g, 2, 3, 4. And then again, because there's nothing between the two letters, it just means multiply, and then x. And then I have 3 of these x's being multiplied. So again, every pair that I have on top and bottom, I'm going to cancel and turn into a 1. So here's 1, oop. All right. So there's 1, g on top and bottom. Here's another g on top and bottom, but there's no more g's on top, so I can't get rid of them. Here's 1 x on top and bottom. Look, it's right on top of itself, so it looks like a 1 now. Here's another x on top and bottom, and here's another x on top and bottom. So, no, don't do that. Okay, I'm going to redo my lines fast. It went away again. Annoying. I don't understand why they keep sometimes going away, but not all of them. All right, let's see if this will work now. So on top, there's no more g's, they canceled away. I still have x times x, 3, there's another one. But then the next 3 x's canceled, but then there's still the one after that. Look, another line went away. Why? Okay. And then on bottom, these 2 g's went canceled. There's still these 2 g's. But then all the x's canceled and became 1s. Now remember, I don't have to write the 1s because it's 1, and times another 1 doesn't change anything. So then, if I wanted to re-put the equations together, I have x to the power of 4, because there's 4 of them being multiplied on top. And then on bottom, in the denominator, I have g to the power of 2. And so this is the same thing as this after I simplify it. So there's always these expectations that you're able to simplify your exponents. And here's how it works. There's 1, 2, 3, 4, 5 rules that you need to learn. And what these rules are the quick ways to do the math and simplify it without needing to do all this crossing out stuff. So here are the rules. First of all, this a in the rule, it's called your base. Like here, your base is 4, and your base is the big number, and then the exponent's the tiny number in the upper right-hand corner. So the rules only work if the bases are the same. Like look here, all of them have to be the same number or the same letter for you to be able to put them together. Because remember up here, you couldn't put the x's with the g's. They didn't combine back together. The x's went with the x's, the g's went with the g's. Like you have to have the same base to use any rule on it. So the first one's called the exponent product rule. And product is just the big word for multiply. So some people like to come in and underneath the word product, write the word multiply. And so if you have some number with an exponent, or some letter with an exponent, being times to the exact same number or letter with a different exponent, you can combine them. Even though you're multiplying these two, you end up adding the exponents. Do you remember that up here? Oh, nope, we didn't do an example of that up here. I'm going to just do one down here then. So if I have 4 to the power of 2, what that means mathematically is that you have 4 times 4. Then it says it's getting times to 4 to the power of 7, meaning that I have 1, 2, 3, 4, 5, 6, 7 more. Oh. I'm not going to show you all of them. Technology. All right. So then if I were to count, how many 4s do I have being multiplied together? Here's 1, 2 from these first two. 3, 4, 5, 6, 7, 8, 9. So in total, they are 9 4s being multiplied together. So I have 4 being raised to the exponent of 9 because it's getting multiplied to itself 9 times. But if you look, that is 2 plus 7. 2 plus 7 equals 9. So even though what we're doing with the numbers is multiplying them, with the exponents, they get added. If we go into Desmos graphing calculator, if I typed in 4 to the power of 2, oh, that's 16, and then times 4 to the power of 7, it's this massive number. And if you look, it's the same thing as 4 to the power of 9. See, exact same number. So note that I'm not asking you to use a calculator and tell me what the number is. I want you to use the exponent rules to simplify it. So I want this to turn into this, 4 to the power of 9. I don't need this as an answer at all on this worksheet or in the challenge questions. If you're using numbers, I'm not asking you to put it in a calculator. I'm asking you to do the math with the exponent rules to simplify it into another expression with a number, with a base number and an exponent. Going back, so in words, the rule is when multiplying the same base number to itself with exponents, add the exponents. All right. Next rule, exponent quotient rule. Quotient is just the big word for divide. So if we look here, if you have a to the power of n divided by the same base to another exponent, it's telling you that you end up subtracting them. This one we did do an example of up here, because if you look, g to the power of 9 divided by g to the power of 4, 9 minus 4 is 5. And if you remember, they get subtracted away because we end up crossing them out because they become ones. So what happens is you just end up doing the 9 minus the 4 on the bottom because they're going to get crossed away. And I could have quickly gotten to g to the power of 5 without writing this all out and having to cross it out. So if I come here, 3 to the power of 8 divided by 3 to the power of 2. If I do a new equation, if I'm just using the rule, it becomes 3 to the power of 8 minus 2, which ends up being 3 to the power of 6 because 8 minus 2 is 6. And because I didn't turn it blue first, it's not going to be blue now. Haha, okay. But if I was trying to go the long way, I could, because 3 to the power of 8 just means that I have 8 on top, 8 threes. 4, oops, 5, 6, 7, 8 in the numerator. And then in the denominator, I have 3 to the power of 2, which means 3 times 3. And now that I have this, I can cross out the 3 divided by 3, make that a 1. This 3 divided by 3 can become a 1. And now that they've canceled away, you can see that I have 1, 2, 3, 4, 5, 6 threes left on top, nothing left on bottom, which means I don't need to write it in fraction form anymore. And it just becomes 3 to the power of 6 that's left. So if we were to type this out, I'm going to copy most of this because it's almost the same phrase. But instead of when multiplying, it's when dividing. The same base number to itself with exponents. You end up subtracting the exponents, because they just end up canceling away. The next one's called the exponent power rule. And power is just another word for exponent. So it's like the exponent rule, meaning if there's an exponent on an exponent like this, what ends up happening is they get multiplied. We did do an example like this above too. With this one, the a to the power of 3, all getting raised to the power of 4. If you remember, if I had 4 of these and each one of these was 3, when we got to the end, there is 12. And 3 times 4 is 12. So if I came down here, and I'm just trying to use the rule only, then it becomes 5 to the power of 3 times 4. And it ends up becoming 5 to the power of 12. Oops. So if I were to paste my little phrase, it's when there is an exponent on an exponent, then you end up multiplying the exponents. If you need to, after every comma, you can write the word then subtract the exponents, then add the exponents. I just wasn't writing it like that at first. Okay. So those are the first 3 rules. I'm going to quickly jump down and do a couple examples on those first 3 rules, because that's a lot, and I want to quickly run through them. So this one becomes, it's multiplying, and remember, when you multiply, you end up adding the exponents. And so 4 plus 9 becomes 13. That's all I need. I don't need you to write it out the long way. I don't even need you to put the 4 plus 9. If you can just do that in your head and then write 7 to the power of 13, that's great. Like here, 10 to the power of 5 times 10 to the power of 3, I add them, so it's going to become 10 to the power of 8. I'm just going to write it out, though. So 10 to the power of 5 is 3 is 10 to the power of 8. Down here, this is now dividing. This slash means dividing, just like this fraction line means dividing. It all means the same thing. All right. So for this one, 3 to the power of 5. And for dividing, remember you subtract, because if they were on top and bottom, it would just cancel itself away. And 5 minus 3 is 2. So it becomes 3 squared. For this one, 4 minus 2 is going to become 5 to the power of 2 once I'm done writing it out. Minus 2, because 4 minus 2 is 2. So that becomes 5 squared. This one is the exponent on exponent rule. And then that tells you that you end up multiplying. So 5 to the power of 3 times 8 ends up being 24. So the answer becomes 5 to the power of 24. This one's a little more complicated because it's combining two of the rules at once. You see you have this 4 on this outer parentheses that has like everything in it. Here, I'm going to change the color of this to show you. Oh, that's an ugly color for reading. Let's go maybe purple. Yeah. So this all goes together, everything in purple. And it's a parenthesis around everything that's being raised to the power of 4. And then on the inside, I have this 3 squared being multiplied, because parenthesis means multiply, if there's nothing between them but the parenthesis, to the power of 5. So you have two rules at once. You're going to often have multiple rules at once. And the point is that in this one, it's almost always better to start with applying the parentheses in first. So meaning I times this 4 to this 2 and to this 5. Because remember, if it's an exponent on an exponent, they get multiplied and it gets put into everything in the parentheses. So both of these 3's need to have this exponent of 4 on it. So what ends up happening is I end up getting 3 to the power of 2 times 4. And then also the next 3 to the power of 5 times 4. Because I need to times that 4 to both of them. So then I have 3 to the power of 8, because 2 times 4 is 8, times 3 to the power of 20, because 5 times 4 is 20. And then finally, because these are getting multiplied now, the rule is that you add the exponents. And so we have 3 to the power of 8 plus 20, which becomes 3 to the power of 28. And that's how you do one with multiple rules involved. All right. Let's go back up and learn the last two rules real fast. The negative exponent rule is just, it goes like this. If a base has a negative exponent, then the term is unhappy. Move it to the other part of the fraction. To make it happy. When I say happy, I mean positive. So let me show an example of this real fast. Every single number in the world, like 9 to the power of negative 3, can be written as a fraction. Because every single thing, always and forever, like 9 to the power of negative 3, you're allowed to divide it by 1. Because dividing it by 1 doesn't change it at all. It's the same, like 5 divided by 1, it's still 5. X divided by 1, it's still X. 9 to the negative 3 divided by 1, still 9 to the negative 3. Just like you're always allowed to times anything by 1 too. So if I wrote times 1 in front of that 9 to the negative 3, power of negative 3, it doesn't matter. Like it's still the same thing. So you can always times by 1, you can always divide by 1, and it turns it into a fraction. And remember, I'm telling you that if the exponent's negative, then it's unhappy where it's at in the fraction. Meaning right now, this 9 to the power of negative 3, it's in the numerator of the fraction. It's on top. It's not happy on top. It doesn't want to be there. It wants to move to the bottom. So I'm going to move it to the bottom. And now that it's on the bottom where it wants to be, it's happy. Don't forget that it's still times 1 because there's still this one here on bottom. So if I'm moving this one down, that one's still there. And then on top, there's still that other one that was there. However, 9 to the power of 3 times 1, still 9 to the power of 3. So I don't need to write it. I can delete that away. So this, in the simplified proper version, is this. Because you should not have negative exponents when you write in a simplified answer. You always need to move them to where they need to go. And so we're going to practice this a lot in a second, but first I'm going to teach you quickly the 0 exponent rule. And basically all it's saying is that anything to the power of 0 is 1. If I go to Desmos, type in 4 to the power of 0, look, it says the answer is 1. If I type in any number I want to the power of 0, the answer is still 1. So anything to the power of 0 is the answer is 1. I'm going to show you why real quick in this nifty little example that combines the rules all together. So on top I have 3 to the power of 8. On bottom, I have 3 to the power of 2 being raised to the power of 4. And remember, the exponent rule means you multiply them. Which means I have 3 to the power of 8 on top still in the numerator. And then in my denominator, the bottom, 3 to the power of 2 times 4 is also 8. So now I have 3 to the power of 8 divided by 3 to the power of 8. Well, because it's the same on top and bottom, and if I were to cancel them all out, it would be 1, 1, 1, 1, 1, 1. All 8 of them would become 1s. Here, I'm going to actually show that. So 1, 2, 3, 4, 5, 6, 7, 8. And then I also have 3 to the power of 8 on bottom. But every single one of them becomes a 1. So 1 times 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 1 is still 1. Because everything times 1 times 1 times 1 times 1 times 1 times 1 is 1. However, if I use my exponent rule for division, the rule says, oh, that's not what I wanted. The rule says that when you divide, you subtract your exponents. What is 8 minus 8? It's 0. So this long thing that equals 1 is the exact same thing as 3 to the power of 0. So 3 to the power of 0 must also equal 1. Which it does. If I went into Desmos, 3 to the power of 0, also 1. Everything to the power of 0 is 1. Everything. Okay? That example, I don't even have examples of this in here. It's just a fact that you need to know that if you ever get anything to the power of 0, it equals 1. But for simplifying, let's do some more simplification problems with negative exponents. These are the ones that are like the ones on your test, where you have to combine all the rules, including the negative exponents, with multiple letters and simplify it to the easiest version you can. So I'm going to show you what to do. So first and foremost, you see this parentheses with another exponent on it. You always want to start with those. So that means you multiply. So x to the power of 2 times negative 3 becomes negative 6. And I have my y. And then on bottom, I have y to the negative 4. Now we move everything that's unhappy and make it happy. And that's always the next thing you want to do. So this x to the negative 6, it's not happy on top in the numerator. It wants to be on bottom in the denominator. So x to the power of 6, now it's positive. You see on top it's negative because it's not happy there. It is happy down below, though, in the denominator. So when I moved it down there, I made it positive. This y on top, very happy on top. It doesn't have a negative exponent. It has a positive 1 exponent. Oh, this is really important. If there is no number on the letter, the exponent's a 1, because there is one letter that's there being multiplied to itself. There's only one of them, so it's not really multiplying, but it's still there. And so this y has a positive 1 exponent, but we don't write it because that's the most common one. And we just leave it on top because it's happy in the numerator. But on bottom, this y to the negative 4, not happy. So I'm going to move it to the top. So on top, I have another y. I'm going to put it in parentheses. Y to the power of now positive 4, because it's now pretty happy, because it went to the top like it wants to be. So then I still have these two y's that I can put together. So this is y to the power of 1 being multiplied to y to the power of 4. So together, there would be 5 y's getting multiplied because you add them. So the 1 from here plus those 4 become 5. And then on the bottom in the denominator, I still have x to the power of 6. I can't combine these two terms. The x cannot combine with the y. They are separate terms. They are separate things. They don't get combined. So this is my answer, my most simplified version. This is the exact same thing as this. You're just rewriting these in a more simplified way using the rules. So let's do this one, which is the most like the test. So to begin, I have this negative 3 on this parenthesis, and I need to put it into every single term in my parenthesis. Give me 1 second. Make it big, make it blue. Fraction 9. Okay. So this 4 is its own term, and it has an invisible exponent of 1 on it, which means 4 has an exponent of 1 that needs to be multiplied to that negative 3 on the outside. W also has an exponent of 1, since there's nothing on it right now, that needs to get multiplied to the negative 3 that's outside the parentheses. And then G has an exponent of negative 5 that needs to get multiplied to that outside negative 3. And then in my denominator, there are no parentheses, so I'm just copying what I have, W to the negative 2 times G to the negative 1. All right. So if I do 1 times negative 3, I just get negative 3. Again, if I do 1 times negative 3, I just get negative 3. But over here, if I do negative 5 times negative 3, I end up with positive 15, because a negative times a negative is a positive. So the next thing I want to do is I want to start moving things that are unhappy. Come on now. So from right here, this 4 to the negative 3 does not want to be on top. It wants to be on the bottom. In the denominator, so 4 to the power of 3 moves to the denominator. Up on top in the numerator, I still have W to the negative 3. It's not happy up there. It wants to go to the bottom, so I'm going to move it down here to the denominator. And W is going to become positive 3 now, because it's happy on bottom. Next in the numerator, I have G to the power of 15, and it's positive, so it's very happy where it's at on top. I'm going to leave it on top. When I look at my denominator, this W to the negative 2, that W isn't happy on bottom. That one wants to go to the top. So W to the power of now positive 2 is going on top, and it's happy there. And then this G to the negative 1, not happy in the denominator, so I'm moving it to the top to the numerator. I'm going to write it by my other G to try to keep my G's together. So the g to the power of 1 is going to go up there on top. And now I have to combine all the letters that are the same by using whatever rule I need to use. So for example, equals. These two g's next to each other, because they're next to each other on the same part of the line, they're getting multiplied. So I end up adding the exponents, and 1 plus 15 becomes g to the power of 16. The w's are on top of each other in a fraction form, which means they're getting divided. So you end up subtracting them. So you have w, and I'm going to actually write this one out because it's a little more confusing, but w to the power of the one on top goes first, so 2 minus the one on bottom. Here's why this matters. 2 minus 3 isn't 1, it's negative 1. Don't forget, I still have 4 to the power of 3 on bottom. But it means I'm not quite done because now my answer has a negative in it. And remember, I told you, you don't want negatives in your answer. So this w to the negative 1 needs to move to the bottom. And when it moves to the bottom, it becomes happy. It becomes a positive 1. However, remember, to the power of 1 isn't actually necessary to write because it just is the exact same thing as w. So now this is my answer, my most simplified version of this crazy thing up here.